I'm here to talk to you about the ins and outs of Elasticsearch and the ELK Stack. So a little bit about Elasticsearch, the company. It was founded in 2012 in Amsterdam. It's venture capitalist funded from a couple of venture capitalist firms, Benchmark, Index Ventures, and NEA. We're a distributed company. Most of our employees are spread throughout the world, working from home, but we do have some offices in Los Altos, Amsterdam, Berlin, London, and Phoenix. And the company itself offers support subscriptions for the products, produces some plugins for the products, and also provides training courses for Elasticsearch and for the ELK Stack, as well as actually maintaining the ELK Stack family of open source products. So a little bit about me. I joined Elasticsearch just over 6 months ago, so May. I've spent 6 years building search applications using Apache Lucene. Have anybody in this room heard of Elasticsearch or Apache Lucene? Okay, good. So I'm an Elasticsearch core developer, so most of my time spent on the Elasticsearch product, creating features. I also teach trainings and answer support tickets. So what is the ELK Stack? So the ELK Stack is made up of Elasticsearch, Logstash, and Kibana. So to go through each one in turn, starting off with Logstash. Logstash is essentially an ETL tool. It manages events and logs, collects the data from a huge number of different sources, parses the data, enriches it, and then stores the data in, again, a huge number of data stores. It's got a very pluggable architecture, so we've got quite a lot of community contributed plugins, and I think we're now up to about 160 plugins spread over sort of these 4 areas of the products. Like I said before, it's open source, provided under Apache 2, and Elasticsearch, the company, actually employs quite a number of engineers to just continually contribute to the product and maintain it and keep the community kind of going. So how does Logstash actually work? There's basically 3 concepts in Logstash. There's concepts of an input, as this is actually getting your log messages from somewhere, or I say log messages, they don't actually have to be log messages. They can be any kind of information, so you could get news articles and parse them through Logstash. You could do Word files, that kind of thing. But inputs consist of things like data stores, so you can actually input data from Elasticsearch or from a database. You can have queues such as RabbitMQ, Kafka. You can stream straight from the network, or you can load from files. And there's actually loads more different plugins, but that's kind of a few of the common ones. You then have a concept of a filter. The job of a filter is to parse, enrich, tag, or drop messages. So essentially, you get your, for example, your web request log coming in on your input, and you can parse that log, each of the log messages, to find out the date, which IP address it came from, what the HTTP method was, that kind of thing. So filters do this parsing, and then you can output that data to, again, a huge number of places, one of which being Elasticsearch, also to queues again. You can have it email people, and a whole host of other outputs are available. So the basic workflow is you might get a message coming in from, say, from a log file. It's got an IP address of 141.1.1.1. You pass it to a Logstash filter, maybe in this case the GeoIP filter, and it'll add on the city and the country that IP address is registered to, and send that out to your data store. Let's say, for example, for this example, that it's Elasticsearch. So the next element in the ELK Stack is Elasticsearch itself. So Elasticsearch is a schema-free REST and JSON document store. It's a distributed document store and scales horizontally very well. Again, it's open source, and again, Elasticsearch employ quite a number of developers to keep the product moving forwards and to drive community contributions and so on. And it works on this principle of zero configuration. So out of the box, we have quite sensible defaults to enable you to get up and running with Elasticsearch in very little time at all. But those defaults are configurable, so when you start getting experience with Elasticsearch and you need to actually customize it for your own specific use cases, there are lots of knobs and dials you can twist to get it working the way you need it to. Elasticsearch itself is written in Java, and it's written on the Lucene, on top of the Lucene libraries. And it's got a very extensible framework, so if it doesn't provide functionality that you need, there's almost always a way you can create a plugin to extend that functionality. So I'm hoping that most people in this room have heard of, seen, and used GitHub. GitHub actually uses Elasticsearch for its search capabilities. So when you search in the box in GitHub, what it's actually doing is sending a request, in this case for the term Elasticsearch, off to Elasticsearch servers, and returns you back a list of results. So this is kind of unstructured search, the basic first feature that you're going to want from any search application. But we actually have quite a number of other features available, including aggregations. So who in this room's heard of facets as a term? Good. So basically, aggregations are kind of like facets, but they go a stage further. I'll go through aggregations in a bit more detail later on, but essentially what it's going to give you is a view onto the results that you can't see. So usually you're going to not return all of your results to the user in one go, because they're not going to be able to process that amount of information. So you can do things like you can say, well, how many of the matching results match Java? This many. How many match Ruby? And so on. And this is done through just asking it, please categorize the languages and how many of the results match each language. So then from this, GitHub actually uses this list to provide structured search. So if you're now interested in just Java repositories, you can click on Java. That will add a filter to your search, and you'll get results in your, the results pane for just Java repositories. We can also enrich the results, so we can show you why it matched your search. Okay, in this instance, we're only searching for Elasticsearch, so you'd hope that everything that came back contained the term Elasticsearch. So highlighting is not particularly useful in this case, but if you've got, say, 4 or 5 terms in your query, it's sometimes useful to know which of those terms actually matched for each document. You might care about some more than others. So that can be quite useful. And also by default, Elasticsearch and indeed Lucene provides results ordered by how well they match your query, so relevance ranked. But you're able to change the sort order and you can sort it by a date field or number field. So instead of the best match, you could sort it by the last updated, so you could get the most recently updated repositories first, or the I'm not sure GitHub actually provide this, but you could get it ordered by the number of favorites that a repository's got. Like I said before, you don't actually want to return every result to your user at the same time. That's just going to be too much information. You're going to end up with a massive web page, which nobody's ever going to want to read. So generally, obviously, you return the top, say, 10 matches, and you allow the user to page through. Elasticsearch actually provides this really easily. And lastly, there's the idea of suggestions. So this is basically, as the user, you probably use this feature if you use GitHub, as you're typing in your search query, before you've even actually pressed enter and run the search, it's coming back with results saying, do you actually mean this issue in this repository? And that can be quite useful for getting your users to the right piece of information very quickly. And the last stage in the ELK stack is Kibana. So Kibana allows you to execute queries in Elasticsearch and visualize their results. So you can add and remove widgets from dashboards. So you can create dashboards with different views on your data, and then you can share, load, and save those dashboards. It basically brings data visualization to business users and allows those users to create or to investigate the data that you've stored in Elasticsearch without actually writing any code. Again, it's open source. So if any of you have seen Kibana, I'm not sure whether you will have, but this is probably what you've seen. I'm not quite sure why it's so dark, but this is probably what you've seen. So on the top here, we've got a graph of requests over time. So you can see that for each of the different queries, we've got PHP requests, image requests, PNG or GIF requests, and CSS requests. You can see how many requests were made to this website over time. We've also got bar chart and a table, just a standard table of terms and how many documents match each of those terms. And the great thing about Kibana is that you can actually, with almost all of these visualizations, you can click on the data that you're interested in and it will refine the visualization to just that. So it will filter down the documents to just those documents. So if you wanted to see what happened here, you could select across this gap and it would change all of the visualizations to just show you that view of the data. It's really good for drilling down into anomalies and actually finding out what's going on. So a couple of months ago, we released Kibana 4 into beta. So this was done, Kibana 4 was written primarily to leverage some of the new capabilities from Elasticsearch, in particular aggregations, which, as I said, I'll go on to in a little bit. But it allows you to do much more complex querying, so multi-line charts, and multi-level pie charts. I think they're called star charts, and stack bar charts as well. And there's a whole host of other stuff coming in the subsequent betas. So who uses the ELK Stack? So this is a list of just some of the users of the ELK Stack. So we've got The Guardian. I actually use it for giving their editors insight into who's reading articles and what's making an article popular and that kind of information. We've got eBay, Perform. Foursquare uses it for the search, for their place searching. PayPal. To go into a couple in detail, GitHub we've already spoken about. They use it for searching their code repositories. TomTom uses the entire ELK Stack, so Elasticsearch, Logstash, and Kibana to centralize viewing of their logs. So it's across their entire infrastructure, they can get a view of what's going on, why is something not working, why does the people from here keep getting 404s, that kind of thing. It's a company called Noble Group who are using Elasticsearch, Kibana, and Marvel. So Marvel is a plugin for Elasticsearch, which allows you to monitor the Elasticsearch cluster itself and provides kind of historic data on what's happened to your cluster. So you can start investigating kind of if you're having issues with running search requests, you can look into why they might be happening. And they're doing analytics on, well, they're scaling up to over 500 billion documents. So quite a lot of data going into that use case. So now you might be thinking, well, how do I use Elasticsearch? So the first thing you're going to want to do is get up and running, installation. It's really easy. I think 2 minutes is probably quite generous, actually. So if you download the distribution from our website, you can get it in tar gzips, you can get it in a zip file. We also have Puppet modules, Chef modules, RPMs, and debs. And you basically just run bin Elasticsearch, and then you're up and running. You've got a single node cluster, which is ready to receive documents and ready for search. So the first thing you're going to want to do after you've got it up and running is find out, is it alive, is it okay? So essentially, most of the time when you would be interacting with Elasticsearch, you'd be doing it through a client. So we've got quite a number of clients that we maintain for JavaScript, .NET, PHP, Perl, a number of others. But just for the sake of simplicity in a presentation, I'm using curl just to do normal REST commands quite easily in the command line. So port 9200 is the HTTP port for Elasticsearch, and if you just do a GET request to that URL, you'll get information such as the cluster name, which by default is Elasticsearch, the node name, which by default it actually picks one of the 300 Marvel characters for you, and it will give you some information about the version of Elasticsearch you're running. So the next thing you're going to want to do is actually put stuff into Elasticsearch. So here we've got a HTTP put request, and we're sending it to this URL. So we're saying we want to store it in the index called books, and we want to store a document of type book, and we're going to give it an ID of 1. And then the payload of the request is just the contents of your document. So in this case, we've got title Elasticsearch Definitive Guide. The author is Clinton Gormley. It was started on the 2nd of February 2003, and there are 230 pages. And Elasticsearch will automatically work out that this is a string and should be tokenized so that you can search for Elasticsearch definitive and guide separately. The author, again, it will do the same and type it as a string. The started field, it will automatically type that as a date and index it as a date, so you can do date ranges and that kind of thing. And pages is already a JSON number, so it will index it as an integer. So if you want to update a document, you actually run exactly the same thing, and you just give it a new payload. So again, we're just saying update document 1 or store document 1, and here we've added a new author, Zachary Tong, and you can actually add arrays, and largely it works. Arrays work the same in Elasticsearch. It's just a single value. So we don't mind whether you give us 1 value or 100 values for a particular field. And when Elasticsearch gets this request, it knows that that document 1 already exists, so it will replace the version with this new version. For delete, you can just use the delete HTTP method, and to get the contents of the document back, you can just use the get method on exactly the same URLs. So how do we actually do a search? So the most basic form of search is kind of your Google one-box style search. So you can do this much like you can on Google, actually, just using the Q query parameter and putting your term or terms in that for that parameter. And what you get back is a JSON response telling you how long the request took on the server, how many shards it searched, how many were successful, and how many failed. And then actually, what did it match? So how many documents in total does it match? And then by default, it will give you the top 10 hits, as we call them, so the top 10 documents, and give you the score for each document, which index it came from, and the payload of the document. So that's all well and good, but that's quite a limited way of doing searching. So we also have what we call a query DSL. So this allows you to do complex querying. So you can do Boolean querying, we can do filtered queries, we can filter on ranges, we can do phrase matching and fuzzy matching. There's some geo queries that you can do. There's a whole host of query functionality, and this is kind of one of the points where you can extend Elasticsearch. So if there's a query which doesn't match your needs, you can write a plugin to add a new query type. So what else can Elasticsearch do? So it can search, but some other features. We've talked about suggestions. There's a backup and restore feature. So obviously, if the worst happens and you lose everything, you can create backups as you're going and then just restore those backups for disaster recovery. It's what's called a percolator, which is kind of a bit of a strange concept at first. Essentially, it reverses the idea of searching. So instead of indexing documents and then running queries against those documents, you index a query and then run the documents against the query. So it sounds a bit weird, but it can be useful for things like, in the previous example where I was indexing books, I may be interested to know when a new book comes in which contains the word Elasticsearch. So what I can do is I can index into the percolator index a query for books containing Elasticsearch, and then when I receive a new book, I can run a percolate request and find out whether it matches that query. And then that could trigger, say, an email to me saying, hey, there's a new book you might be interested in. It's called whatever. There's geo, like I said in the previous slide, there's geo features. So we can do things like, so we can index geo points and geo shapes. And then we can do queries such as, give me all the documents whose location is within this distance of this particular point. Or we can do searches for documents which are within or intersect a particular polygon. So you could actually have a polygon for the United Kingdom, and you could say, show me all documents which are located in the United Kingdom. There's loads of monitoring APIs, so we give loads of information not only about the Elasticsearch, not only about Elasticsearch itself, such as the indexes and the nodes, but also about the JVM the nodes are running on and the OS. So there's loads of stuff that you can get out for the current status of your cluster. And actually, Marvel, the monitoring tool I was talking about previously, that actually uses these monitoring APIs and then stores the results of them. And lastly, one of the most exciting features, as far as I'm concerned, aggregations. So like I said before, aggregations are like facets, but they have more power. Essentially, they have more power because they can be nested. So they add more dimensions to your facets. So this gives you really deep analytical insights into your data and allows quite complex visualizations. So just showing you an example in Kibana 4, this is actually log data. So I've got the number of HTTP requests over time on the x-axis. I've got time on the y-axis is number of requests. And each bar represents 1 week of data. So what we've done in a single pass of the documents is group together all of the requests into little buckets of, into weekly buckets, and then we've plotted that on the graph. So that's great, and that's exactly what facets can do. So what? Aggregations can go further than this. So what I've done now, in one request, I've asked Elasticsearch to put all of the documents into weekly buckets, but then further split them into what I've called response code groups. So 200 responses, 300 responses, 400 responses, 500 responses. So we haven't got any 500 responses. They'd probably be the most interesting ones, but unfortunately we haven't. As we'd expect, we've got lots of 200s, which is good. Our website's working pretty well. We've got some 300s. They're probably redirects. Probably don't mind too much about those. And we've got some 400s, which may or may not be okay. Some people ask for pages which don't exist anymore. That might be okay. So from this, we might have some stuff to investigate down here, but we don't really know. So we can go a stage further again, and we can get we can add a new dimension to the aggregations and split each of these weekly bars up into the country that the request came from. So it's a bit hard to see on here, but the green bars are the United States. So they get the majority of the 200 requests. So I'd say our website is probably most popular in the United States. But the more interesting bit is down here with the 400s. You can see, hopefully, that the brown and the pink bars keep popping up everywhere. And actually, I can't see brown or pink bars at all up here, so they must be quite low numbers. So brown is actually Canada, and pink is China. So it might be worth So this kind of gives us an indication that it's worth investigating what's going on with requests coming from China and Canada. There seems to be something wrong with the website in terms of users who are trying to use it from that place. And it gives you, in one request to Elasticsearch and one pass through all of your documents, it's given you a good indication of where the point that you might want to look for your website is. So that was in Kibana 4, but you don't actually have to do these aggregation requests in Kibana. You can just send them to Elasticsearch and get back a JSON response. Obviously, Kibana gives you a nice visualization mechanism for the results. Looks good on a slideshow as well. So how does Elasticsearch scale? So we've got Elastic in our name, so you'd hope that we can scale. So we work on the principle of scaling up, out, not up. So essentially, from whatever state you're in, if you need more performance, add more machines rather than trying to add performance to your current machines. So to do this, you need to shard your data. And sharding your data is largely transparent in Elasticsearch. It's good to know that it does it, but you don't actually see it day to day. So basically, when you index your data into one index. And what happens underneath is one index is actually made up of many shards. So each shard is a standalone Lucene index. Works exactly the same as any other Lucene index, but it only stores a portion of the data that you're you're storing in this index. So we need a combined view when we search. So in Elasticsearch, there's a concept of a node. A node is just one running instance of Elasticsearch, usually relates to a single server. You can actually run multiple nodes on a single server, and you can do that just by starting new processes. You don't have to do any configuration. You just start a new, you do bin.elasticsearch in a different terminal, and it'll start a new node, and that will join the cluster. We also have the concept of a shard, as I said, which is just a bucket of data. It's the physical worker unit of Elasticsearch, and it lives on a single node. And an index is a logical namespace, and it points to one or more shards. So this is just the calculation we use to work out which shard of documents stored on. So we take the ID of a document, we take some hash of the ID, and then we modulo it by the number of nodes, the number of shards in your index, and that tells us the shard ID. So I'll skip over this quite quickly because it's not massively interesting, but essentially if you index a document with ID 1, we'll run this little calculation, and it will tell us that that document should be stored on shard 2, and we store the document. So that's done by us. You don't have to know which shard to go to. We'll work that out for you. Same with getting a document. It'll run exactly the same calculation, and it will return it back from the correct shard. For searching, we don't actually know which shards your documents are located on. If we did, we'd be able to return them without running a search. So what we do is we actually go to every shard, and then we just combine the results. So how do we scale elastically, though? So generally, you'll start small. You'll start with, say, a single node. You've got a single index, 3 shards. You may want to add more nodes to enable you to store more data or to balance the load, especially the indexing load across more nodes. This node could get overloaded with indexing tasks, so it's good to split it across more nodes to enable you to index more data. So if you add more nodes, they'll join the cluster. Elasticsearch will automatically migrate your data, so you end up in a balanced state, and your nodes are actually the requests are more balanced across your nodes. When you add a new index, we'll automatically allocate the shards so that they're balanced across those nodes as well. But the problem is that more data means more hardware failure. So 3 AM on Sunday, this might happen. We've lost shard 0 of the green index and shard 1 of the blue index, and that data's gone. We don't have a backup. It's completely disappeared. Either we have to go back to our original source and re-index it, or we have to deal with the fact that we've lost the data. So that's obviously not a good situation to be in. So what do we need to do? We need to add redundancy. So for every shard, make a copy. So we have primary shards, which are the main shard, and we have replica shards, which are just a copy of the primary shard. There's nothing special about them, apart from the fact that they're not a primary shard. They store exactly the same information. So when you have one node, when you start indexing, you're going to have, say, 3 shards in your index, and they're all going to be primaries. There's no point in us putting replicas on this node. We wouldn't actually be adding any redundancy, so we don't bother. When you add a new node, what Elasticsearch will do is that node will join the cluster, and we'll realize that we don't have redundancy at the moment. We'll start copying the primary shards across to your new node and give you redundancy. If you add a further node, in this instance, we've said we only want one replica per shard. So we don't actually need to add any more replicas, but it's still not balanced. We're still not using node C. So what we'll do is we'll migrate, for example, one primary and one replica across to the new node, so that we end up in a balanced, redundant state. So now if we lose a node, we've still got a copy of shard 0. It's not a primary, but it's still got all of the data. And what we can do is just promote that to a primary, and then we can reallocate the replicas so that we end up in a rebalanced, redundant state. So like I said, the primary is just a role. It's just, primary shards don't contain any more special data. They're just told that they're primaries. The reason why we need a primary is that they receive the document changes first. And then they forward these document changes to the replicas in parallel. The number of primaries are fixed. So when you create an index, you tell it how many shards you want that index to contain. And that can't be changed. However, telling an index to have more shards than the nodes in your cluster is perfectly fine. You can have an index with 10 shards, but only have 5 nodes. And then when you later scale up, you can make use of those extra nodes because you can then spread the shards across all of your nodes. So a replica shard is just a copy of the primary shard. And it still serves read and search requests, and it still indexes data. It just indexes the data after the primary. The number of replicas can be changed, and it can be changed dynamically. Actually, the Guardian uses this feature to make them scale up very quickly and automatically when they get peak usage on their system. They can just change the number of replicas to add more when they've got more usage and remove them when that usage then comes back down. And the more replicas you have, largely the more read throughput you have if you have more hardware. So it's no good adding replicas if you've got no hardware to put those replicas on. It's not going to give you any performance gain. But if you've got the hardware, more replicas will give you more read throughput. The problem is who controls everything. So you've got to have somebody to allocate these shards, and that's the master node. So like I said, a node is just a running instance of Elasticsearch. But a cluster is one or more of those instances, so one or more nodes, all with the same cluster name, which are working together. So a cluster might look like this. You've got node A and node B. They've both got the same cluster name, so they're both formed in a cluster together. When you start a new node, just by running bin Elasticsearch, that node will use multicast or unicast, by default multicast, but you can set it up to use unicast instead, to detect the already formed cluster and join it. And like I said earlier, you don't want to know which one of these nodes you need to send your request to. That would be quite difficult as a user to work out. So what you can do is send your request to absolutely any node in the cluster, and we'll forward it to the correct node, and then return you back the response. So how do we do this? Every node in the cluster knows where every document is. I don't mean this by every node has a list of all of the documents, but every node has what's called the cluster state. And this is cluster level information. So it tells you which shards belong to which indices and which shards live on which nodes. And this is the information that we can use to work out where your documents actually are. The cluster state can only be updated by the master node. So when you start a new cluster, in this instance with a single node, you start it up, it will form a cluster on its own, and it will elect itself as the master. When you add new nodes to your cluster, they'll join, and because the master's already been elected, they'll just join and they'll know that node A is the master. But again, the master node is just a role. So if the master fails, then node B and C will detect this failure, and they'll re-elect a master, and everything's still available. You can still do indexing. It can still rebalance your shards, and everything should be fine. So the master node only manages cluster level changes. So you might think there's a bit of a bottleneck because everything's got to go through the master node. But actually, it's only things like shard allocation and when shards disappear that the master node actually really gets involved. For document level changes, like just normal searching, it doesn't actually have to pass through the master node at all. So what does this actually give you as a result? So we get a distributed real-time search analytics platform, which works the same way on your laptop as it works on your 1,000-node cluster. So if you want to know any more, you can check out our website, elasticsearch.org. We've got blogs, case studies, there's comprehensive documentation, there's videos. We also have webinars that you can sign up to. Thanks for listening. Are there any questions? Elasticsearch itself doesn't do that. You can produce you can set up your fields so that you can have different fields with different languages, and you can push, say, French into one field and English into another field. But we don't actually do the detection of what the language is and the extraction of that language. Something that Logstash in theory could provide. I'm not sure there's a plugin that provides it currently, but it's something that I think would live better in kind of pre-Elasticsearch ETL type application. Anyone else? There is the concept of a binary field, obviously, and I have actually heard that there are people using it to index images, to then do image search. Out of the box, there aren't the analyzers for images, but there are plugins for it. Yeah, and in terms of actually storing the data, like I said, there's binary fields, so you could store the video in Elasticsearch. It's just you'd have to provide the metadata to be able to search it. Anyone else? For Elasticsearch, Logstash, and Kibana, no. It's completely free and open source. You can even contribute back to us if you find a bug. For Marvel, it's provided as a commercial plugin, and is actually provided with the support subscriptions for free as well. So I'm actually not sure whether there's current integration with Umbraco, but in terms of websites, because there's a JavaScript client, obviously you can communicate with Elasticsearch through the JavaScript client from your website. In terms of whether there's anybody who's working on Umbraco integration, I actually don't know. Sorry. Scalable. You should be able to add nodes to kind of when you hit a wall of performance, because it's not like you're going to stop responding. It's just going to be, you're going to get slower and slower and slower. When you hit a limit to what you're comfortable with as a response time, if you add more hardware, we can. But I mean, the majority of searches are generally sub-second. So you're talking about a really fast response time. So there's Marvel for monitoring your index and finding out that determining, say, you've got shards which are unallocated or something's gone wrong. There are also other plugins that you can download, such as Elasticsearch Head, for example. Gives you a good idea of it gives you a good idea of what's stored on each node, and basically the cluster state that I was talking about. It kind of gives you a visual representation of that cluster state. So there's quite a lot of plugins out there to show you different aspects of your index.